Today we are going to discuss a few problems mostly related to distribution function. Basically the first problem would be a function of distribution functions, and we will try to see whether we can check, or we will try to see whether that function would be a distribution function. There are few techniques involved, we will explain eventually. And the second problem would be another interesting one. We will give a concrete example of a distribution function, and just to keep the suspense, I am not going to tell you what is going to happen, but a very interesting thing will happen, and that interesting thing, although a little weird but surprising, and at the same time if you look at the graph of the distribution function, it will be immediately clear. So what we are trying to emphasize, that it is not that only studying the distribution function that is not the main thing, but at the same time, in order to understand the distribution function, we also need to look at the graph of the distribution function, which might reveal many important informations. So we are now going to discuss a few problems on distribution functions. So we are going to discuss few problems on probability theory. So let's start with the distribution function. So this problem is taken from this book Gunmukta Dasgupta. So this is the first problem that we are going to discuss. And as usual, first problem should be a very easy one. So the problem goes like this. Let f1, f2, fk be the distribution functions, and a1, a2 and so on ak be some real numbers or scalars, such that summation ai equals to 1 and 0 less than equals to ai less than equals to 1. That means ai's are all positive quantity but less than or equals to 1. Then we have to show that then if we define another function capital F as summation fi I equals to 1 to k, then we have to show that this f is also a distribution function. Now in order to show this, we have to remember or recall the properties of distribution function. So what are those properties? So first we have to prove that f is a distribution function. That means we have to show that some necessary conditions that a distribution function would satisfy. The conditions are, as you can remember, first one is f is a non-decreasing function. And the second one consists of two properties. One is limit f of x equals to 1 when x goes to infinity, and limit x goes to minus infinity f of x equals to 0. That means fx goes to 1 as x goes to infinity, and capital Fx goes to 0 as x goes to minus infinity. And the last one is very interesting, which ensures that fx is a right continuous function. Fx might be a continuous function, but it must be a right continuous function. That means there might exist some distribution functions which are not continuous but necessarily right continuous. So now we are going to prove these properties one by one. So let's start with the first one, that is f is a non-decreasing function. Now first note that it is given in the problem that capital Fi is a distribution function for each I. Now here I moves on 1 to k, so let's consider I is fixed, and then for fixed I, Fi is a distribution function. Now since Fi is a distribution function, we can immediately say that if we take two numbers x1 and x2 such that x1 is less than x2, then because of the fact that Fi is a distribution function, we can immediately write capital Fi x1 is less than or equals to capital Fi x2. Now this is true for every I equals to 1, 2 and so on to k. So this comes directly from the property of a distribution function. So we have to show that this property will be satisfied by capital F, that is summation Fi. So let's start with capital F of x1. So that means we have to show that capital F of x1 would be less than or equals to capital F of x2. Now capital F of x1 is nothing but summation I equals to 1 to k ai capital Fi x1. Now Fi is a distribution function and just from the above line we can immediately write, or we can replace capital Fi x1 by capital Fi x2, but there should be one less than equals to sign. So this quantity is less than equals to summation I equals to 1 to k ai capital Fi x2, and if you look at this quantity, this is nothing but capital F of x2. So that eventually proves that f of x1 is less than or equals to x2 whenever x1 is less than x2. So we can immediately say that f is a non-decreasing function. So the first property is proved. Now let us consider the second property, or rather the first part of the second property. That is, now since again Fi is a distribution function for every I equals to 1 to k, then limit x goes to infinity Fi x equals to 1. Again, limit x goes to infinity fx equals to limit x goes to infinity. Now replace fx by summation ai Fi x. Now remember, this k is a finite quantity, so this is basically a finite sum. So we can easily bring this limit inside the summation sign, so that it becomes summation I equals to 1 to k ai limit x goes to infinity Fi x. And again, limit x goes to infinity Fi x is just 1, because Fi x is a distribution function for every I, and that means it goes to 1 as x goes to infinity. So this gives us only summation ai equals to 1 to k, and by the condition of the problem that summation ai is always equals to 1, given condition of the problem. So this proves that limit fx x goes to infinity equals to 1. Now we are left to prove that fx equals to, or fx goes to 0 as x goes to minus infinity, and the proof is very simple, and it follows exactly in the same manner. Like if we put x goes to minus infinity, and then here also limit x goes to minus infinity summation ai Fi x, summation is nothing but a finite sum I equals to 1 to k, because k is a finite number. So we can bring the limit inside the summation sign and limit Fi x equals to 0 as x goes to minus infinity. So this becomes very easy to, and we can immediately see that limit x goes to infinity, minus infinity fx equals to 0. So all these properties are satisfied except one, and which is one of the most interesting properties of distribution function, which is that we have to show that capital F must be a right continuous function. Now in order to prove that, again note that since capital Fi is a distribution function for each I, we can immediately write limit h goes to 0 plus, that means h is coming from the right side of the 0, so that means it is a right hand limit. So limit h goes to 0 plus Fi x plus h equals to Fi x, because Fi is a right continuous function because it's a distribution function. Now this is true for every I equals to 1 to k. This is very important, that whenever I'm saying that something is happened for Fi, that means it holds for I equals to, for all I equals to 1 to k. So now the proof is again very simple. Limit h goes to 0 plus f of x plus h equals to limit h goes to 0 plus summation I equals to 1 to k ai Fi x plus h. Again, there is no problem in bringing the limit inside the summation sign, because k is finite, that means this is a finite sum. So this entire quantity becomes summation I equals to 1 to k ai limit h goes to 0 plus Fi x plus h, which is equals to, that means since Fi is a distribution function, and we have already seen that Fi is a right continuous function, so this limit is nothing but Fi x, which immediately gives us the expression summation I equals to 1 to k ai Fi x, which is nothing but the definition of capital Fx, the way we define capital Fx. Now this is true for any x. We have not put any restriction on x. So capital F is right continuous for every value of x, which means all the rather four properties of capital F, or the distribution function, are satisfied, and here we can immediately say that capital F is a distribution function. So hence the proof of this is complete. So it is very easy to see that we have just checked whether capital F satisfies all the properties of distribution function, and here the proof goes like that. Now we move on to another interesting problem on a distribution function, which is due to Pearson. Pearson actually defined or gave one function, capital Fx equals to 0 when x less than equals to 0 and equals to 1 minus 2 by 3 e to the power minus x by 3 minus 1/3 e to the power minus third bracket x by 3 or box of x by 3 whenever x greater than 0. Now box of x or third bracket x is defined as the largest integer contained in x. That means if x equals to 2.3, box of x would be 2, and again if x equals to 2, box of x would be 2. So that's the way we define box function. Now the question is, can we say that f is a distribution function? And if so, if we can show that capital F is a distribution function, so we need to check the graph of f. How does f look like? You will see that it's very interesting graph of f. And we need to calculate how to calculate the probability that 4 less than x less than 6 and 4 less than x less than equals to 6. So it is very interesting to note that here one probability expression contains x less than 6, another x less than equals to 6. So we are going to evaluate this thing or investigate this problem one by one. But first we should check whether capital F is a distribution function or not. Now again, in order to prove or check capital F is a distribution function, we have to check whether capital Fx satisfies all the properties of a distribution function. However, if it fails to satisfy even one property or one of the 4 properties, it will not be a distribution function. So remember, whenever you need to see whether capital F is a distribution function, we have to check that whether capital F satisfies each and every property, that is all 4 properties of a distribution function. So let's start one by one. Now what about capital Fx as x goes to infinity? Now this is equals to limit x goes to infinity and the entire expression 1 minus 2/3 e to the power minus x by 3 minus 1/3 e to the power minus box x by 3. Now clearly, as x goes to infinity, e to the power minus x by 3 is 0. E to the power minus box x by 3 is also 0, because as x gets larger and larger, e to the power minus a very large quantity, which means that it will be arbitrarily small, and hence the limit is 0. So ultimately the limit is equals to 1. Similarly, we can immediately check that capital Fx goes to 0 as x goes to minus infinity. In fact, it is exactly equals to 0, because we have defined capital Fx as capital Fx equals to 0 whenever x less than 0. Now minus infinity, you can arbitrarily think that it's a very large negative quantity. So as x goes to minus infinity, Fx is always 0, and hence the limit would be 0. Now we have to show that we have to check whether capital F is non-decreasing. Now for x1 less than x2, that means take 2 numbers x1 and x2 such that x1 is less than x2. Then minus 2 by 3 e to the power minus x1 by 3 is less than minus 2 by 3 e to the power minus x2 by 3, and minus 1 by 3 e to the power minus box of x1 by 3 is less than equals to minus 1 by 3 e to the power minus box of x2 by 3. Now it is interesting to note the equality sign. In one case there is no equality sign, but in another case there might be equality sign, because if we take x1 equals to 3 and x2 equals to 3.2, that means x1 is less than x2 strictly, then x1 by 3 is less than x2 by 3, but box of x1 by 3 is equal to box of x2 by 3, which is in fact equals to 1, because box of x2 by 3 is box of 1 point something. That means box of that is the largest integer contained in that, and that something is a fraction, so it is equals to 1. Therefore, it is clear that capital F of x1 is less than capital F of x2 whenever 0 less than x1 less than x2. Now remember, we have taken these two numbers as positive, and hence there is a strict inequality. But if we take two numbers x1 and x2, both are less than or equals to 0, and x1 is less than x2, then fx1 equals to fx2, because in this case fx is defined to be 0. So it is clear that whenever we take two numbers x1 and which is less than or strictly less than x2, f is a non-decreasing function in x. Now I am not going to prove this that capital Fx is right continuous. It is very easy to see that capital Fx is right continuous, and hence we can immediately say that capital Fx is a distribution function. Now one interesting thing is that although we get capital F as a distribution function, but we cannot get any probability mass function or any probability density function from this F. So this is a very nice and peculiar example of a distribution function for which neither PMF nor PDF exists. This claim will be immediately clear if we just look at the graph of capital F. And here is the graph of capital F. If you recall that the function capital Fx, there is a box of something that is x by 3. That means whenever x is a multiple of 3, it is a pure number, but if x is slightly larger than the multiple of 3, then again box of that quantity or box of that x by 3 would be that multiple of 3. So there is a jump. As soon as it reaches a number 3 or 6 like that, there is a jump, because all other numbers which are slightly less than 3 or 6 or 9, there is any multiple of 3, it is not getting the value of 3. It is getting the value either, if the multiple of 3 is 3, the box of x by 3 it becomes 1, and like that. But as soon as it reaches the multiple of 3, there is a small jump, and hence there is a point of discontinuity. But it is easy to see that even at this point the function is right continuous but not left continuous. So there is a discontinuity, and hence for this kind of graph it is clear that we cannot get neither PMF nor PDF. Another interesting thing that we can observe immediately, if we want to calculate the probabilities of two events, probability 4 less than x less than 6 and probability 4 less than x less than equals to 6. Let's calculate this one by one. Recall that capital Fx is 0 whenever x less than equals to 0 and equals to 1 minus 2 by 3 e to the power minus x by 3 minus 1 by 3 e to the power minus box of x by 3 for x greater than 0. So probability 4 less than x less than 6, we can immediately write that, remember, capital Fx is defined as probability capital X less than equals to small x. So we can immediately write this quantity as f of 6 minus h minus f of 4 plus h when h goes to 0, because there is no strict equality sign in either of this end. And just put the value of, instead of x in the distribution function, put 6 minus h and we will get this expression, and again put 4 plus h, we will get another expression. And if we take the limit as h goes to 0, then it is clear that 6 minus h by 3 becomes 2, but box of 6 minus h by 3 in the limit becomes 1, because 6 minus h by 3 is nothing but 2 minus h by 3. Now remember, 2 minus h by 3, since h is positive, is a number which is less than 2. So the largest integer contained in that number is 1. So the power becomes e to the power minus 1. Exactly similarly, we can say that box of 4 plus h by 3 equals to 4 by 3, that is 1 point something plus h by 3. Now this quantity 1 plus the number, that is again smaller than 1. So this quantity becomes 1 when we take box of that quantity. So eventually, if we just simplify this, we get this value, and which is in fact 0.08551. Now remember this value 0.08551. I will come back to this value number later. Now let's calculate probability 4 less than x less than equals to 6, which is again f of 6, because there is an equality sign. So if x less than equals to 6, so f of 6 minus limit h goes to 0, f of 4 plus h. Again, if we remember the distribution function form, just put instead of x put 6 and instead of x put 4 plus h. Just by simplification. Now remember, here it is 6 by 3 box of that. Initially it was 6 minus h by 3 box of that. So this becomes 2 in this case. Initially it was 1. And if we do little bit of simplification, we will get the value as 0.16302. Now the earlier value was 0.085 and this one is 0.163 like that. So it's nearly double. So the number is changed just by adding one number. So here we cannot say that this function is continuous at 6, but there is a slight discontinuity, or rather it is only right continuous at 6. So this gives a nice example of a distribution function where we cannot find any PDF or PMF corresponding to that distribution function. So we have seen that in order to check whether a function is distribution function or not, it is enough to check all the 4 properties. But remember one thing, we have to check whether it satisfies all the properties. It is not that if it fails to satisfy even one property and we can say it is a distribution function. It is not like that. We cannot say that. So whenever we say that this function is a particular function, is a distribution function, we have to ensure that it satisfies all the properties of a distribution function. In the second problem, the interesting thing is that we have studied, or we have seen that the given function is a distribution function. We have checked all the 4 properties and it satisfies all the 4 properties, and hence we have concluded that this is a distribution function. But our common belief is that we can always find a PMF for a discrete variable and for a PDF for a continuous variable. Actually, it should be an absolutely continuous variable. But unfortunately or fortunately, because it reveals a very interesting thing, that for this distribution function we cannot find a PMF, or we find a PDF. So we give an example where distribution function of random variable exists, but neither PMF nor PDF exists. And interesting to see that it is immediately obvious if you look at the curve or the graph of the distribution function, because there are certain points when the x value is a multiple of 3, we say there is a discrete jump which actually violates the continuity of the distribution function, thus making it impossible to find a PMF or a PDF.